Hello, everybody. I'm pleased to present our in-person speaker, Professor Alan Selinger. Hello to everybody here on campus, and hello to all of our online attendees. I'll start off with a intro to Professor Allinger. He received his bachelor's in science and chemistry from Eastern Michigan University in 1989. After 2 years as a research associate at Gelmo Sciences Incorporated, he obtained his PhD degree in 1997 from the University of Michigan in macromolecular science and engineering under the guidance of Professor Richard M. Lane. He then moved to Sandia National Laboratories in Albuquerque, New Mexico for his postdoctoral work with Professor C. Jeffrey Brinker. From 1998 to 2003, he worked as a research scientist in the Industrial R&D Laboratories of Cannon Research Center Americas, Palo Alto, California, and Obsys U.S. Corporation, Fremont, California. From 2003 to 2008, he held the position of senior scientist at the Institute of Materials Research and Engineering, IMRE, under the Agency for Science, Technology, and Research, Republic of Singapore. He then moved to Stanford University from 2008 to 2012 as both consulting associate professor in materials science and engineering and executive director of the Center for Advanced Molecular Photovoltaics. Since 2012, he has been a professor of chemistry and materials science at the Colorado School of Mines and senior scientist at the National Renewable Energy Lab. His research interests are the synthesis of new hybrid materials for the application and high surface materials for gas storage and catalyst supports, light emitting diodes, photovoltaics, thin film transistors, and scintillation, radiation detection. We're going to take questions at the end. So if you have questions, post them in the Q&A as normal, but we'll address them at the end. And with that, I'll hand it off to Professor Alan Selinger.
Thank you for that introduction. And yeah, my talk will be on scintillators, but as mentioned, we work a lot with basically organic semiconductor materials that can be used in a variety of applications. So our group are very much synthetic organic polymer chemists. So I'm not a nuclear engineer, I'm not a nuclear scientist. It just happens that our materials have application in that area. So I've been kind of learning about this whole technology. And I'll kind of give some background on how I got into this as we go along. So this is the title, and these are images of things that we've made with our scintillation materials. These are all, of course, done through printing and additive manufacturing. I won't talk about that project in this talk because that will be talked with Professor Manfredi, I think, in a couple of lectures. Our biggest effort right now is actually in making new organic glass scintillators, but that's also going to be covered tomorrow by Tessa. So I'll just briefly touch on that, but that's kind of the area that we're going. So before I get into the science, I just wanted to give a little bit more of where I come from, because Colorado School of Mines is maybe not everybody's familiar with it, but if you can see here, it's very close to Denver. So it's located in Golden, Colorado. There's Boulder. And all of this is the Rocky Mountains. So we're really right up against the foothills of the Rocky Mountains. We're celebrating our 150th anniversary. So there's all kinds of things going on at our university. So relatively small, so about 5,400 undergrads and 1,700 grad students. That usually fluctuates a couple hundred. And it's basically a STEM school, so it's almost entirely engineering students with chemistry, and I think economics are the only sort of non-engineering departments. And so we're, pretty highly ranked. It's pretty tough to get into the school. We also, of course, I have to dig on Michigan State. So, we actually have more women engineers graduating than Michigan State, and also the total number of engineering majors is more than Michigan State. So you can see that even though it's like a really small undergraduate population, we're basically like a school of engineering. So we're graduating lots of engineers, and it's a pretty nerdy campus. Students are all pretty serious. And what else? Oh, yeah, and about 5 years ago, we became an R1 research university. So now we're competing with the big boys. And so we have, even though we're pretty small, we have a pretty large research budget. So it's a really cool place. And so like you can see right up against the Rocky Mountains. So this is what it looks like around our campus. This is our central diag sort of area of our campus. This is like just off campus when the sun is coming up in the morning. This is about a 5-minute drive west. Just park, take these hikes. You can even get to stuff like this just hiking from the university up the trails. And so this is actually in Golden in the fall and in the winter. And then this last one is kind of a cool place. So we go with my research group to this place. It's called St. Mary's Glacier. It's about 45 minutes drive. We leave Golden, it's about 90 degrees. We get up here, it's about 50 degrees. And basically we can have snowball fights in August. And so we walk up this glacier all the way up to the top. And so this is a 20,000-year-old glacier that's unfortunately receding, but still there. And we can still play around in it. So come out and hang out. It's a pretty cool place. All right, so I will be talking about plastic scintillators and how we can improve the properties of plastic scintillators as chemists and how we can improve on the fabrication of plastic scintillators. So when I got into this game about 10 years ago, I had no idea about this technology, and I kind of just took a step back and looked at it as a chemist, and I thought there were a large number of bottlenecks and low-hanging fruit that we as chemists could start to try to handle. And it turns out there's not a lot of organic synthetic chemists in this area. So it was a unique opportunity to have some collaborations with folks that are active in the nuclear area. So one of the things that I'll talk about is how we designed new plastic scintillators that have a property that's called cross-linking that basically makes a more compact, more solid scintillator that minimizes diffusion of dopants within the scintillator and aspects like that I'll go into. We also try to deal with issues that we see in plastic scintillators by using dopants that can be actually reacted into the matrix. So I'll talk about that. And I probably won't get to the polysiloxane scintillators, but that's just a way that we can make scintillators like in 3 hours versus the usual like 10-day process that's with plastic scintillators. And then I'll talk about how we can use alternative methods for processing. In this case, we use a photo-initiated process rather than a thermal process to make the scintillators. And by doing that, we can also improve on the processing time. So yeah, I'm told that many of you out there have some knowledge about why we need these materials, but I'll just briefly touch on it. So these scintillators are usually, they usually exist at ports of entry, at airports, at international borders, and there'll be one of these towers that is filled with a scintillator, and they're screening for nuclear materials inside of containers, for example. So whether it's somebody trying to do something bad or if it's just naturally occurring radioactive material, these series of detectors are aimed to find those. So if it's anything giving off neutrons, then that's usually an indication that there's bad things in there and that those containers need to be inspected. But there are times when containers are filled with things like bananas and avocados and kitty litter and granite, and those have enough accumulated radioactive materials that can set these things off. So kind of the holy grail is like, how do we distinguish between materials that are benign and materials that are nefarious? And so that's kind of where plastic scintillators come in. So there are a variety of materials that are used to detect these types of nuclear events. So there is helium-3. And so this is, I'm just kind of showing my interpretation of the pros and cons. So these are good for detecting nuclear materials. I classify them as not ambient stable because they'll just evaporate and go out of the atmosphere. I would think that the scalability and the economics of these are pretty expensive just because you have to encapsulate the gas. There's also single crystals. These can be inorganic or they can be organic. They're also very good at detecting and distinguishing between neutrons and gammas. Some of these have some ambient stability because they just absorb water and they can become foggy. It's pretty tough to grow crystals, so they're expensive and usually tough to scale up. There are liquid scintillators, and these are pretty good as well. Of course, those need to be encapsulated as well. That can be scaled, but ambient stability, I guess if they're encapsulated is probably good, but they also are tough to manage, tough to handle because they're liquids, and so maybe not economically viable. And so that's kind of where plastics come in, and I should have another column here, like a subtopic of the organic glass scintillators. That's sort of in between plastics and single crystals, I would classify as. So plastics maybe, historically have not been that good in terms of comparing to the other materials for detecting neutrons and gammas, but they are stable, they are scalable, and they are very economic. So it's a pretty big space right now for people like me as chemists to make an impact. And so that's kind of how we got into this game, was looking at issues with plastic scintillators. So this is basically how they work. So this is a piece of plastic. It's irradiated with neutrons or gammas. When it does that, it absorbs that energy and transfers that energy down to a luminescent material. The luminescent material gives off light, and that light is detected by a photomultiplier tube or some kind of a photodetector, and then it gives you some type of a signal. And so we'll talk about what that signal is. So that's basically how these work. These plastic materials interact with ionizing radiation, and they do it in different ways, so you can get different peaks that are associated with either a neutron or a gamma source. So basically, the matrix, the primary component of these materials are polymers. These can be things like polystyrene or polyvinyl toluene. So everybody's heard about polystyrene. They're just commodity plastics. Within that matrix, there is some kind of a dopant, and so that dopant is responsible for getting the radiation that partially comes into the matrix. And there's a series of energy transfers that allow for the dopant to acquire all that energy, and then eventually that transfers energy to what's called a wavelength shifter or a secondary dopant, and then that's the light that is detected by the detector that's on the scintillator. So basically, these are the three main components, and I'm talking about just kind of plastic scintillators that you can buy off the shelf and use. And these are the primary types of scintillators that are used in all those portal monitors that I showed in those yellow boxes next to the truck. So again, the radiation sources come in, they excite the polymer matrix. The transfer of energy from the matrix to the primary dopant is mostly a non-radiative process, but there is some radiative processes involved. So all that energy goes to these primary dopants. And when you're talking about a process that I'll about in a second called pulse shape discrimination, the dopant concentration can be upwards of 20 weight percent, 25 weight percent of the total system. And I'll talk about why that is. And then it basically transfers all the energy to this wavelength shifter, and then that will be detected. So that's basically how these work. So the primary function of the matrix, again, is to absorb the incident radiation and transfer the energy to the primary dopant. Criteria is that these need to be optically clear. So they can't be opaque, they can't be cloudy, they have to be like water clear. They need to be able to solubilize the dopants, and they need to have some aromatic character. So when I say aromatic, I mean these cyclic rings here. They are very important in the absorption of the radiation and the transfer of that energy throughout the system to the dopants. And so it turns out that materials that don't have these aromatic rings don't perform as well. So it's pretty well known that in order for a plastic material to work as a scintillator, it has to have some aromatic component. So the function of the primary dopant is to actively also to absorb radiation, ionizing radiation. It's also fluorescing, so it has to have some kind of a high fluorescent quantum yield. It should generate singlet excited states and triplet excited states. And it also, that triplet energy state needs to be mobile so it can diffuse. It needs to be soluble in these matrices upwards of 20 to 25%. The spectral overlap between the secondary dopant needs to be high. So as these materials fluoresce, all of that energy needs to line up with the absorption band of this wavelength shifter, and then that's absorbed by the wavelength shifter, and then that emits to the detector. So that's the primary function of the wavelength shifter, is that it is the absorbing in the range of the primary dopant, and it doesn't have any self-quenching, and that it needs to have a spectral overlap with the actual detector. And so from my understanding, when I got into this game, I thought, this is awesome because I can just make, it's actually a lot easier to make green emitting dopants as a chemist. But the green emitting dopant doesn't align with the photomultiplier tubes that are currently used. And so right now we are only focused on making these blue emitting dopants because of photomultiplier tubes. But my understanding is that silicon photodiodes and other types of light detection is getting better. And I think that will open up this field even more, because then we can make green emitting dopants and yellow and red emitting dopants. And then that should all be able to be captured by next generation detection sources. All right, so this is kind of talking briefly about how these detectors discriminate between energy sources like neutrons and gammas. So when a neutron comes in, it interacts with these scintillators in a certain way. So this is a time on the x-axis, and we're kind of looking in the nanoseconds to microsecond range here of the excited state. So you can see the shape of a neutron interacting with a plastic scintillator is different than a gamma. There's more of a fast response with a gamma, slower response with a longer tail with the neutron. And so generally there is what's called a longer delayed excitation that happens when a neutron interacts with an organic material like a plastic scintillator. And so you can set a cutoff time. So this is also something that the community probably needs to generalize on. So everybody is measuring this the same way. So we can all just pick the time that is the best, and everybody uses that time. And then we can distinguish the difference between the long component and the prompt component. And then that can be translated into a curve like this, where you generate two curves. One is associated with neutrons and one is associated with gammas, and all that comes about because of just the signal time from the excitation. And so the distance between these lobes is usually defined as a figure of merit, and that figure of merit kind of has to be above a certain value. So sometimes people talk about 1.37 as a value. That is, you have to be higher than that. So the bigger the separation, the better. And so this term of being able to differentiate between neutrons and gammas is referred to as pulse shape discrimination. And so that's one of the important properties of these materials that we've been working on, and that Department of Energy has been interested in funding. Again, to be able to distinguish between gamma sources and neutron sources. So when going back to this matrix, you can see that upwards of 70 to 80% of this matrix is basically the commodity polystyrene-based materials. Another 20 to 30% is this primary dopant, and then all of that energy is then funneled down to something that's there at only 0.1%. So these are really efficient dopants that can absorb all that energy and emit. So it's pretty amazing. And then the other thing you need to worry about is that, you know, if all of the energy is being transferred to 0.1%, then all of your materials need to be ultra pure, because you can always have some impurity there. That impurity then could be stealing all of these radiation sources, and maybe if the impurity is not an efficient luminescent material, then that's going to be a lost pathway and you get a lot of quenching going on. So these things need to be very pure. So as chemists, we need to worry about that quite a bit. All right, so these plastic scintillators that are capable of doing this PSD have some problems. So I'm talking about like if you just go and buy, I think some of these materials have been addressed, but in the early days, if you were to just go and buy a plastic scintillator that had PSD capability, it had issues. And so one of those issues is that you can see from this orange curve that you're getting a better FOM, so you're getting a better separation between the neutrons and gammas as you go to a higher dopant concentration. So that's getting better and better and better. But as you add more of this PPO, you can see that the hardness of these scintillators is dropping drastically. And so what happens is that at 0 or 1% of this PPO, these materials are pretty hard, like a really hard plastic. And then down here, they become like the consistency of like a gummy bear or something that's really soft. And so that is not good because that eventually these need to be big slabs of material that need to hold their own weight. And if you have soft material, of course, it's going to deform. And also when it's soft, you have this 20 weight% of dopant that's just blended into the polymer. So that's going to diffuse and aggregate. And so those are all the types of things that we see. So we started to wonder how we can deal with that. So there's low glass transition temperature, there's softened plastic, and you can see that this is basically 20 weight% of the PPO. So that is about here, 25 weight%, and then 30 weight%. And so this is basically like if you make these, they're water clear. If you let them sit around for a while, they slowly, you can see like dopant nucleate because it's diffusing. They like to find each other and aggregate and grow. They eventually become these opaque, useless materials. So that goes back to how these plastic scintillators are made. So basically, a polystyrene comes from the monomer unit of polystyrene, which is styrene, and that's a liquid at room temperature. It's basically like a solvent. So you basically fill, and this is how we do it. Of course, this is not how industry does it, but you have some vial of material. In this case, it's filled with this liquid monomer, like vinyl toluene or styrene. In some cases, you use what's called a thermal initiator to get the polymerization process to start. And so this is a image of how we do this. So we have these vials, we put them in an oven. There's this liquid down there, and we slowly heat these things up for 5 days because this is a highly exothermic reaction. So if you heat it up too fast, it will exotherm out and explode. So this needs to be done very carefully. And it takes us 5 days. I'm told that the company that everybody buys from, Elgin, the process takes like 10 days because they're dealing with enormous amounts and they can't have these exotherm runaway reactions. So, anybody from a production standpoint that is doing something that takes 10 days from start to finish is not happy. That takes a lot of time. You're heating these ovens for long periods of time. And again, these are flammable solvents, these liquids. So you're dealing with like these potentially toxic flammable materials. So it's not nice. So even our lab would just get really stinky at these pretty relatively low volumes that we're working with. And it's not nice. So it's time and energy intensive. These systems are oxygen sensitive, so you have to do all this under inert atmospheres as best you can. And then of course you're limited by the form factors because you can just pour this in and then you can't really do much with that. So, we started to look at this and say, how can we handle this? So the material challenges are how do we deal with this soft material? And so one way that we're tackling this, again, is with this cross-linking approach or with this polymerizable dopant approach. We also have this polysiloxane project, and then we have this photopolymerization project. So I'm going to start off with the cross-linking and polymerizable dopants. So the idea here is, how we can improve the material properties. Basically, how do we limit or make these systems hard as we increase the dopant concentration to have pulse shape discrimination properties. So one way is that we can introduce what's called a cross-linking agent, and I'll talk about that in a second, and that will just make a more rigid matrix. And you know, sometimes I like to give the end of the story at the beginning, so it works. So that's kind of what happened. This was a successful project and resulted in some nice papers and some patents and things like that. So so it works. So again, this is the curve that we're trying to fix. So this is an example of something that's called a cross-linker, because in the case of styrene, polyvinyl toluene, there's one vinyl source, and that leads to linear polymers. When you have something that has more than one reactive species, then that will quickly form these network structures. So it no longer will form linear structures, it forms these networks. And once you form these networks, then that results in more rigid type materials. So we wanted to have these cross-linking systems that were at least bifunctional. This leads to the increased hardness. In theory, also has these aromatic electrons, because again, we want to have this aromatic content to interact with the ionizing radiation. And so I'm just going to quickly show some of the results. So this is basically with 0% of this cross-linker, 20% dopant. This is kind of what I showed you before. As you increase the concentration of PPO, these eventually become cloudy. When we start introducing this concentration of this cross-linker at 1%, 3%, 5%, 8%, you can see now these become clear. And the reason is that these matrices are again becoming very rigid, and it's preventing these dopants from being able to easily diffuse through the system. So in this type of system, when there's no cross-linker, it's just linear polymers. These dopants are able to diffuse and find each other and aggregate and crystallize. But when we stabilize the matrix, they don't do that. And so all of these systems, then when we get to this 8%, they're nice and hard, and they're much more stable. So now the question is, do they still work in terms of what we want them to do? So is their figure of merit still good? So the answer is yes, because this is the value that we ended up getting. That was the image that I showed before is from one of these materials. And this is an example of one that doesn't work. So this is just varying that PPO concentration and showing you visually what it means when an FOM value is below 0.9. You can see that these lobes come closer together, and so it just becomes harder to see that. When you separate them, of course, it becomes a lot easier, and so that's a better material. So we always compare these in terms of light yield and figure of merit to commercial materials. And so this is light yield of a material that we compare it to. This is a commercial scintillator that we can use to compare light output. And so in this case, I think our light output was a little bit less. So when I'm talking about, I'm gonna show the hardness of these in this value called Shor D. And just to kind of give you an idea of where this hardness needs to be, it's sort of in this hardness area where you can see it's kind of like a hard hat at a construction site or a shopping cart wheel or a shoe heel. They're kind of like, that's the hardness. And then this is the kind of hardness that we were getting, that you can get when you don't have these cross-linkers way down here. So, all right, so this is kind of what we saw. So as we increase the PPO content, we don't see a big change in the FOM, which is great. So we can actually have the PPO content quite high, and these are really good values. Even this 1.5 value is probably good enough. The light yield is still pretty good compared to the source that we're comparing it to, and then you can see that the hardness is where it needs to be. So with the 30% PPO, you really need to increase the cross-linker to get the hardness back up. So it's hard, it works well, good light output. So this is a kind of win. We did a lot of other work. We looked at a lot of different cross-linkers. We looked at some cross-linkers that are fluorinated to make them more hydrophobic. So that worked really well. We looked at contact angles and water fogging. One of the issues in the early days was if these scintillators are exposed to humid environments, they become foggy. And so that was one of the reasons why we were working on cross-linking materials to make them more hydrophobic, to prevent water ingress into these scintillators. So yeah, this all worked, and so that was fun. And this was all work that was done through the ETI, which is an NSA-funded consortium. So now we got to that value of a good situation, but the issue there is still all that 20 to 25% of that primary dopant is still just physically blended into that matrix. So in theory, it could still diffuse. And so that was one thing we wanted to deal with. So we handled all this, but we don't know how to deal with this dopant aggregation and leaching. So that was the next topic we wanted to do. And so one way that we did that was, can we synthesize dopants that have some kind of a polymerizable site so they can be chemically integrated into the matrix? And again, the results are that yes, we could do that, and it worked pretty well. And so this is where all the chemistry comes in. So we basically, this is PPO. So we knew that PPO is the dopant that everybody uses. So we wanted to work with PPO first. So we figured out a way to make PPO with an OH group on it. So once it has an OH group on it, then that is a site where we can put a functional group. So in that case, we put this methacrylate group. So now this is PPO here, it's methacrylate here. So in theory, it is a reactive PPO. And so you can see the yields are quite high. So this is a feasible process. And so again, the idea is that we have this polyvinyl toluene monomer, we have this reactive dopant, we polymerize this all up, and then now this dopant is chemically integrated into the backbone so it can no longer diffuse. So unfortunately, the first reactive dopant we made had some solubility issues, and so it could not be dissolved in that system. And so that didn't work. So then, okay, so we go back to the reaction flask and we figure out what we can do. And so we go through the same process. We stop this precursor 1. And in that case, we just add basically an alkyl chain on here. So we add like more degrees of freedom. This is considered to be like a flexible unit. So we just push this OH group out here, and then now we put the methacrylate group out here. So here it's with 2 carbons, here it's with 3 carbons. So we made these 2 alternative reactive dopants. They both have the PPO, they just have a little difference in the spacer length between the PPO and the reactive methacrylate group. So now you can see that with the ethyl bridge and with the propyl bridge, you can get to a point where you can actually add 48% of these, and they're pretty good in terms of their optical clarity. So, and then again, these are super hard, as I'll show in a second. So we have these systems. So now if we look at the figure of merit, PPO is this one. So this is just blended in, but as we know, these are becoming soft and they're not very stable. So with our propyl system, this is the blue line, we can get up to like 1.6-ish FOM values. And with the ethyl bridge, we can get up to like 1.4-ish almost at these weight percentages. And so it's not as high, but I think it's still in that visual range where the separation is actually still quite good. And the hardness is, all 3 of these are hard throughout. So again, dopants are not, they're integrated into the matrix and the glass transition temperature. So this is basically just a thermal experiment that we do just to show when the matrix starts to move. And so all of these are at good temperatures. All right, so the next question is, are these dopants actually chemically linked into the matrix? And so one way that we do that is through this experiment that's called a Soxhlet extraction. So we have some solvent down here. And so in this case, it's just ethanol because PPO is soluble in ethanol. And so we have this little thimble here. So we put the scintillators inside these thimbles and we start heating up the solvent. The solvent will come up, it will fill up this reservoir, and then it will drain down. And so over a period of like 24 hours, this can happen like 30 or 40 times. And so you're just accumulating anything that's leaching from the scintillator down here. And then we concentrate this, and then we look at it and see what has come out of the scintillator. So we put, some sample up there, and we, look at different things. And so here is our 25% of our propyl methacrylate PPO. So basically nothing came out. Same with the ethyl, same with the system that was not soluble. But when we just have physically blended PPO, you can see that PPO is coming out. So our system, they don't come out, so it must be chemically linked in and not diffusing out and not leaching out. So that's a good sign. So basically, this again was a successful result. What we did find is that even in our system, if you use different, more aggressive solvents like THF or chloroform or something, you can actually get unreacted vinyl toluene. So there's still like buried in the matrix some monomer that hasn't been integrated, and so that's coming out. And so I think that may be a potential issue as well, that we're trying to look at. So there are examples in the literature of scintillators that have unreacted monomers inside that can lead to issues. So that's one thing that we still need to figure out. The other thing is that we as a group have been working on different dopants besides PPO. So we've been working on what's called phenylfluorine, that's this unit. So we've been more recently been making dopants, reactive dopants based on this phenylfluorine fluorescent dopant with methacrylates and even styrenyl units, because we also know that sometimes these methacrylate units are not good for light output. And so we kind of are looking now more towards these styrenic units as reactive systems. All right, so this project has worked, and it's still an active project in our group working on reactive dopants. And again, this is published work, and it's these type of dopants that we've also been using in our additive manufacturing project as well. So I think from here, I'm going to jump to the photopolymerization project and skip the polysiloxanes. So again, most of these cross-link systems I've been talking about, I think we can reduce that time a little bit because they are reactive. They're forming like gel materials and solid materials much quicker than this 5 days. So in those systems, I think we can get away with like 3 days. But we haven't really pushed that. I think we could probably get it lower. But in any case, we think that bringing this timing down is only going to be helpful for a production standpoint. People want to always reduce the cost of production. So if you drive something from 10 days to 1 day, it's got to be cheaper. So the first way we tackle this is with a process called photopolymerization. So the question is, can we make these plastic scintillators that can be cured not with a thermal process, but just by shining light on it? So these photopolymerization systems have been shown in other examples to happen very fast. And so, yeah, it has worked, but it's still an active project in our group. So this kind of goes back to the, for my PhD here at Michigan, I worked on dental materials. And with dental materials, for composites, that's all done with light curing. I don't know if any of you out there ever had a filling done with one of these and they're shining that blue light in your mouth. This is exactly what's going on. So there are monomers there. In the case of a ceramic, filling, it's mostly some kind of a silica and zirconia filler. that is integrated in, and it's kind of like this toothpaste consistency. The reason, so if you take some of these filler materials, you dilute them with some reactive species, you can get it into this toothpaste quality that you can fill and shine light. And so this is exactly what's happening. So you're basically taking a monomer, cross-linkers, some kind of a photo initiator, you're mixing it with this silica or zirconia, and then you're polymerizing everything in an environment with oxygen, with moisture, and doing it super fast so that it can cure, in your mouth. And in reality, these photons can only penetrate a certain distance. So when they do these dental fillings, they usually have to do it in a series of like 4 or 5 steps. They put down a thin layer, they zap it, they put down a thin layer, they zap it, because if they put it too thick, photons can only reach a certain penetration depth. And so that means that things are not curing down below. But this is exactly the chemistry that we started with. Use these same types of photo initiators that they use in the dental composites. So we basically made solutions, and we went on eBay or Amazon and got some light source that matched up right at the point where these photo initiators are cleaving to form radicals to start these reactions. And we made these super water clear samples. So we just made these solutions. We put them, as I'll show in a second, and we could make a full functioning plastic scintillator in less than 24 hours. So we reduced it basically from 10 days down to 1 day. So this is, this crude system. So we have like a chamber that's covered with mirrors, and we shine the light on it. So all the photons are bouncing off. And so, yeah, we just shine the light on there. And, if you reach in there and you touch that vial, it's actually pretty darn hot because, again, it's exothermic. So it's kind of a combination of photons that are doing the curing and the heat. It's kind of propagating everything as well. So yeah, this whole project, we were able to reduce process from 5 days to 1 day. And let's see. So yeah, so now if I show some of the results, so the yellow lines, the blue colors, of course. So the yellow lines are the thermal process, and the blue lines are the photo process. So in terms of the figure of merit, you can see it's slightly less, but maybe within experimental error. The light yield is slightly less, and the hardness is slightly less. And so we know the reason for that, and that's because we do have a lower degree of polymerization, and we're able to extract out, 2% of unreacted vinyl toluene is pretty significant. So this is something that we're trying to handle now versus the thermal initiated process, which is much less. So still in the works. Yeah, okay, so this whole system works. It uses existing technology. So, this is something that I think a company like Elgin could simply just put some lights, shine it on their process, and it would. So we're talking with Elgin to see if they're interested, and it seems like they may be. What else? Yeah, so this kind of course, extended into the additive manufacturing, because additive manufacturing is basically using photons to cure things. And so all of this chemistry has sort of transferred over to the additive manufacturing, but I'll let Professor Juan Manfredi talk about that. Won't steal any of his thunder. Yeah, so all of this works with the existing dopants, with the reactive dopants, and so we've gotten this to work quite well. Okay, so 10 days to 1 day. We've also gotten this to go from 10 days to 1 day to like a few hours, and that's by completely changing the matrix. So this is the traditional plastic scintillator system. It uses polystyrene based, but we've actually gone and used a silicone or a polysiloxane, which is commonly like the stuff that you use for caulking. It's also kind of the Mobile One oil, like in your car, the synthetic oil is based on polysilicones. So that's kind of what we're talking about. And so these systems are more elastomeric to rigid. The process is not air sensitive. So these are basically silicones that you can go and buy. And so that's exactly what we did. We bought silicones and we tested a whole bunch of them out, and we wanted to see whether we could use these aromatic silicone systems to be used as plastic scintillators. So the idea there was to see, because we know that these systems cure very quickly, and so can we transfer that to a plastic scintillator system? So this is some of the early work that we did. We're still kind of working in this area, but we tested out a bunch of different silicones. We have the commercial PPO dopant. We have this new dopant that we like. And we just took, these are viscous liquids. We dilute them a little bit with some solvent. We add in the dopant. We add the dopant up to 5 weight percent, which again is 5 times less than in the traditional plastic scintillator systems. We add in some secondary. And I swear, like, the reason why this project started is because the person who was running ETI, Professor Anna Erickson, before the ETI project came on board, we met at a conference and she was talking about how she wanted to make a polysiloxane elastomeric scintillator. She said she couldn't get them to work. And then I realized it was because she was using a polysiloxane that had no aromatic content. So I went back to the lab and I myself went in the lab and I had some stuff. I poured it. I reacted it for 3 hours. I sent it to her and she's like, oh my God, this is working great. And so that's kind of how this whole thing started. So basically these are, they're like little Super Ball type materials. They're pretty soft. But the amazing thing is that you can get this pulse shape discrimination property at much lower dopant concentration. So like at 5 weight percent, you're getting these to actually be quite good in terms of light output and pulse shape discrimination. It's not perfect. This is early days and we're still working on this. And so in some cases, the light output can actually exceed that of the commercial samples. And so in this case, our phenylfluorine dopant works much better than the PPO. In the plastic scintillator system, the PPO works better than our phenylfluorine. So these are all like, we don't know the reason, but there's definitely differences. And all of these again is just put them in the oven at 150 degrees. It's just like baking a pie. Just throw it in there, 3 hours, pull it out, and it's done. So this seems to me like a really encouraging result too. And the last thing I want to talk about, just to show, we are familiar with Patrick Fang's work. We are collaborating with Patrick Fang. We know that he has these materials, but of course, that is tip of the iceberg. There is probably, 100 other materials out there that could be excellent organic glass scintillators that can be made a lot easier. And so we've just basically the first 3 organic glass materials we made that I'm calling ABC here because we haven't published on this. One of them didn't work, one of them didn't work, and then one worked great. So this is already just an organic glass that we made in our lab. We shipped it off to Patrick. We got a quite good PSD and so we have basically now like 10 promising materials in our lab that we're going to be sending off to Patrick to test in this area. So we're hoping that this area will kick off as well. So that's it. 48-ish minutes, did it? This is the team that's working on this. This guy Tristan's working on some organic glasses. Uran's working on reactive dopants. Dina's an organic glass person. Caleb just graduated. Ashford's working more on the PV, and these guys are undergrads. So that's it. So I hope you guys learned something, and I'll be happy to take any questions.
Well, thank you so much for that excellent talk. Yep, thank you so much for that excellent talk. I'll open it up to the room here in person for questions first. Aaron, I see you have some questions in the chat, so if nobody has questions right now here, we'll get to Aaron's. Will,
You can start. Okay.
Yeah, you mentioned that using a, what is it, a green simulator would be easier. Is it like easier to manufacture? Does it easier to get a higher light yield?
Yeah, I mean, it's just as a chemist, there's a lot of avenues to make really efficient green fluorescent materials. You know, like in my early days as a researcher, I worked on organic LEDs. Everybody knows what an organic LED is. I mean, that's like the display that's in your pocket now, and it's like that expensive, beautiful TV at Best Buy. And that's what we did. And so for those OLEDs, the blue that you're seeing and the green and the red and all the color that you're seeing in organic, that's an organic material that's emitting light from electrical stimulation. And so green is the easiest dopant to make. It's just like from a chemistry standpoint, it's easy. And also it's a lower energy. So a blue emitting material is, you know, sometimes if you're kind of in that deeper blue, you know, that starts to stress out the molecule quite a bit, you know, so like you're emitting, you know, if these things are like in an OLED, the light that you need to see, it's putting a lot of stress on the molecule. And so if it's emitting blue, that's kind of stressing out the bonds. And so there's differential aging in an OLED though. The blue pixels usually die out faster because it's higher energy. So green is just perfect. And your eye actually is most sensitive to green. So yeah, that's kind of what, you know, but I hope silicon photodiodes take over PMTs, because I think that would be a really neat avenue to explore.
And I also wanted to ask, you mentioned that you wanted hydrophobic crosslinkers. Why would you want hydrophobic properties? Isn't like a plastic simulator where you like coated hydrophobic coating?
Yeah, so you know, my understanding is when these plastic simulators go in these portal monitors, there is some encapsulation, but I don't think it's that great. And there was like some of the Elgin products that were being used in the portal monitors, like people started to realize that the portal monitors were becoming less and less efficient. When they opened up those cases, they realized that they had all become pink. And so people didn't realize what was going on, and it was basically water was ingressing into the porous polymer. And then like the freeze thaw, it was getting stuck. And then that was causing like a change in the refractive index, and it was making these things foggy. And so then they had to replace out a lot of those portal monitor scintillators. And so that there was like, I remember we all met in Washington, DC. We've got to tackle this immediate problem. And so there were a bunch of different ways to do it. And one was to make the plastic scintillator more hydrophobic, so it's tougher for the water to penetrate into it.
Thank you. That's all I got.
So we've got some questions online. Erin, would you like to ask your questions in person?
Oh, yes. So I'm familiar with what you're talking about with dental materials. I had sealant put on teeth to prevent cavities, and they cured it with the with the black ultraviolet light. But there's also gel nail polish, which cures under a UV light. Do you know if that's like the same photo activator? And if it's not, like, have you explored that other photo activator?
There are lots of different photo activators. Our system, you know, like in these scintillator formulations, there's a lot of dopants that are absorbing photons. And so we basically have to choose the system where our dopants are not stealing all those photons. So there's like little windows that you can choose in order to make this work. So like in a dental system, there's no PPO and there's no secondary dopant. So some of these lights, the photoinitiators interfere or don't work because all the photons you're sending in are actually absorbed by the PPO or the secondary, and then are not able to be used as a photoinitiator. That turned out to be a big problem in our additive manufacturing, is finding, because in additive manufacturing, there's very few. 365, there's 385, there's 405, so we needed to find a system that worked because of the dopants that were inhibiting the reaction. So like, I don't know, you're talking about blacklight. Blacklight is usually 365, so those are probably different systems. This what I showed here is 470. It's like a really blue light. Blacklight is usually like 365 or something.
Also, when you are curing these compounds under the light, like, do you have like an agitator mixer while it's curing so that things don't like, diffuse and cure and get trapped?
Yeah,
Or does that do more?
in our system, in the early days, the student would just go in every 15 minutes and turn it a little bit. But then we ended up getting one of these, again, like something on Amazon or eBay, like something that we put it on a stage and it just slowly spun it. So that it would, yeah, that's a good question. So we can kind of have more homogeneous distribution of the photons. But yeah, but by virtue of, we still had unreacted monomer, it's probably some of the photons were not able to get into the interior.
I wanted to ask about how you quantify the hardness of these, like what kind of test does one put the material through in order to get a numerical value for hardness?
Yeah, so these are kind of qualitative, so we didn't use like any, instrumentation. It's basically like, it's almost like a pen, and it has like a tip on it, and then you just press the button, just gives you this value. It's kind of like a pretty crude way of doing it. I mean, we probably should do it more quantitatively, but we were just kind of looking more for qualitatively, just by feeling it, you could just tell too. But yeah, it could be something to explore later.
We have some questions online, one from Professor Manfredi. He says, thank you for the excellent talk. Can you explain why, from a chemical perspective, PPO is such a good fluoro? Is there other good candidates out there that you think could have comparable scintillation properties without the leaching?
Yeah, so basic, so PPO, again, it's still baffles me. Looking at the chemical structure, I would think that this would be a completely planar molecule that wouldn't have any solubility. So first thing is I'm just amazed that you can solubilize it in these systems to the degree that you can. Second of all, yeah, it just has this great property for pulse shape discrimination. So it's amazing, and something with the triplet states and the diffusion. And it's really small. So I think that's a problem that makes it easier to diffuse. So in like our organic glass project, these molecules that we're designing are physically much bigger. When the molecule is physically much bigger, it's more difficult to diffuse. And so PPO is very two-dimensional and small, so it can just move around. So the molecules that we're designing now are more three-dimensional and big, so the diffusion is much less, but then maybe PPO is great because it is planar and small, so I think that may be one of the reasons why our reactive PPO systems maybe didn't work as well in terms of pulse shape discrimination, because it wasn't able to form like the perfect structure like it can when it's just really in. Yeah, that's kind of one of our goals, is to make bigger molecules, to go this OGS route to prevent diffusion, minimize diffusion. PPO is magic. It's like always the first one that they chose worked. It worked for like 60 years.
There's one question that says, how much time does it take to synthesize plastic scintillators using the photosynthesis?
Yeah, so that was like a couple hours. I mean, so basically we shine light on it for a couple hours. Yeah, so here we basically, in early days, we just expose it in this light source for 2 hours. And then once we do that, it kind of gets into a gel state. So you can turn the vial upside down and it doesn't move, but it's still like jiggly. Then that's when we put it in the oven. And so in that case, we can put it in the oven at a fairly higher temperature because it's in the gel state. It's a lot of the reactivity has been used. And so you don't get those really high exothermic reactions. So, yeah, so, I think we can do this for like 1 hour and 12 hours. And so we're kind of, we can get this to work, but again, the issue is that we still have unreacted monomer inside that we need to deal with. But yeah, so we do these reactions the traditional way using a 5-day system, but I was at a conference in March. The guy from Elgin said, oh, no, it takes 10 days. And they pour it into these enormous, first they do like a pre-polymerization process. They take all the monomer, they put it into these big reactors and they heat up the reactors without any thermal initiators. And they stir it at high temperatures until it gets to the right viscosity. So it gets to be like syrup, and then they pour it into these enormous molds. And then they wait for the bubbles to diffuse out, and then they put it in these ovens, like very carefully heated up. Or, like, I can't imagine. So this is the way it's done. I'm also a big fan of like why, we're starting to look at polystyrene is a very mature technology. Like there's hundreds of different grades of polystyrene. So why can't we just use polystyrene and just blend it with dopants? So that's another area we're looking into. And that's kind of what Patrick Feng has shown recently, that he's able to blend his OGS with polystyrene pellets, and it works. And that way you don't ever have to deal with, believe me, I'm a chemist. I've worked with thousands of different chemicals, and our lab really stinks when we're doing these experiments. And even though they're in vials, they're in ovens, just a tiny bit of the stuff into the lab, and the styrene monomer really stinks. Vinyl toluene really stinks. So I can't imagine what that Elgin plant must smell like. Yeah, and then you have to worry about the workers, right? They need to be safe too. So.
Not to spoil Professor Manfredi's talk too much on Thursday, but you talk about here it's like 2 hours and then a 24-hour cure for these photopolymerized scintillators. We were fortunate enough to go out a couple years back with Dr. Febraro and make some of these with him with photopolymerization and thermal polymerization, and he showed us the 3D printing process, right? Where you do a layer and then you cure it and do another layer. For these smaller detectors, is that layering process, like, would that improve your polymerization? Like, would you have less left over, or is it a pretty similar amount?
Oh, to go back and check for unpolymerized?
Yeah.
Yeah, no, we haven't done that. It's a good idea. Yeah, we should take those parts, do one of those leaching studies to see.
Yeah, that'd be interesting.
Yeah, I think that the additive manufacturing, I think would be beneficial for that. Because it's a pretty high flux of photons in that additive. It's way more than what we're doing system. Cool.
Yeah, I was kind of thinking maybe it's like a penetration issue too, right? With the
Yeah.
photons, but
Yeah, because again, like a lot of dopants in there are stealing photons away from what they're meant to be doing in our system.
yes, I see a few other ones, but I think we've mostly answered. Did you want to do that or?
I think, yeah, I know we're a little past time. If you are willing, any other questions that people have, I know they could probably reach out through email.
Yeah, for sure. I can answer if you forward me all the questions.
Yeah, for sure, yeah. And thank you all so much for listening.
Thank you, Professor Selinger, and
Thank you.
we'll be back tomorrow, and Tessa will be talking about her project on organic glass. End of the week, we'll have Professor Manfredi talking about other work with plastic scintillators like 3D printing and such, and excited for both talks. Thanks. See y'all.